Alright, welcome to the third and final part of the Putting It All Together lesson. Incidentally, this is take 3, so if I seem a little impatient, well, now you know why. Alright, so we are doing this third and final example problem. It is split into 2 parts, but notice that the function that we're actually integrating is the same in both parts. So let's be on the lookout for parts of, or for work you did in part A that you can reuse in part B and hence save yourself a lot of time. From the get-go, it doesn't look like we can integrate this particularly easily because none of our integral identities include tangent. But with a little bit of algebra and some tricky u-substitutions, you can actually solve this using the knowledge you already know. All you have to do, or the key thing to do, is to rewrite tangent as sine over cosine. Once you do this, you can either say u is equal to sine 2x, or you could say that u is equal to cosine 2x. You can solve it both ways. In general, when you're doing a u substitution, if the numerator and denominator look equally complicated, go with the denominator. This applies not just to this problem, but generally. Also, this is one of those cases where you could do the u substitution either way. Either u is equal to sine 2x or u is equal to cosine 2x. But if you choose u is equal to sine 2x, you will dive into a rabbit hole of rather weird calculus for this level of complication. You'll have to substitute for u in 2 different places, and then you'll have to do a u substitution on top of your u substitution, which I guess would be called a v substitution, and it will be a lot of work. Probably twice as much work as making u equal to cosine 2x. So, knowing that ahead of time, let's just set u is equal to cosine 2x. Alright, starting with this, you take the derivative of both sides. Alright, so we got our dx on this side. Now, in this case, we have a function inside of our function. So 2x is a function inside of the cosine function. And that means, since we're taking a derivative, that means we have to use the chain rule. Okay, so that's the derivative of the outer function. Now let's take the derivative of the inner function. Well, derivative of 2x, that's pretty easy. That's just 2, or 2 times x to the 0. Alright, rearrange this a little bit. And isolate dx out of this. Alright, now we do the big ol' substitution. This stuff here becomes u, and this stuff here becomes dx. Alright, I'm going to try to do a Salcon style color coding of what we end up with here. So let's see, we start with green, and that's our f of x equals integral, and I didn't change the sine 2x at all. But we are dividing by not cosine 2x, we're dividing by u. And then dx gets replaced by all this stuff here. Okay, cool. That all seems to have gone off reasonably well. And what you see immediately is that the sine 2x's cancel each other out. And so what we are left with then is capital F of x equals integral of negative 1 over 2u. Well, we can factor the negative 1/2 outside. Don't forget the du. And so this is going to be negative in, there we go. I can correct it a little bit there. Negative 1/2 times 1 over u du. Okay, integral of 1 over u du, that's easy. Don't use the power rule on this. It's a 1 over u du, or 1 over x dx pattern, so that's natural log of the absolute value of x. So we get f of x equals negative 1/2 times the natural log of the absolute value of u plus c. Last but not least, back substitute the u back into here, so this is going to be f of x equals negative 1/2 times the natural log of the absolute value of, we'll do this in orange, cosine of the quantity 2x oops, that should be in green here, plus c. Alright, so we are done with the general solution. However, we have enough information here to do a specific solution, to find a specific solution, so we're going to go ahead and do that. Now, this is going to take a little bit more room than I have, so I'm going to steal some room from part B here. And actually, part B does not take a whole lot of space, so I'm going to steal all of this space from part B. Deal with that, part B. Alright. Now, what this says is that wherever I see an x, I can put a pi. So that becomes pi right there. And what this says is wherever I see an f, we can put a 4. So we start out with 4 equals, alright, negative 1/2 times the natural log of the absolute value of cosine of the quantity 2, and the x becomes a pi, plus c. Okay, so that is plugging these specific values into this function. Alright, cosine of 2 pi. Well, think about a cosine function. Looks kind of like this, and then starts high, goes low, and then goes high again. Alright, so, and a full period is 2 pi. So this is just 1. So this is going to be 4 equals negative 1/2 times the natural log of the absolute value of 1, natural plus c. Natural log of the absolute value of 1 is 0. So this is going to be 4 equals negative 1/2 times 0 plus c. All this becomes 0, and so that means 4 equals c. Okay, then we take this, and we take that, and substitute this into here in order to get. Let's see if I can keep the amazing Technicolor function up. F of x equals negative 1/2 times the natural log of the absolute value of, switch colors, cosine 2x, switch colors back. Switch colors again. Plus 4, although black is technically not a color. Alright, so this is going to be our final answer for part A. Now, if you noticed, We are at the 10-minute mark and we are only done with Part A. However, Part B is much easier, because remember, the first thing you do in order to calculate a definite integral is you calculate the general solution to the corresponding indefinite integral. Well, we got that right here. This thing down here is the general solution. So we can skip that and just plug this in. So normally we take the general solution, we forget about the plus c, and then we put the boundary values out here like this, and the general solution goes right here. So we'll just do that same thing, except we won't actually do the calculus because we did all the calculus over here. Now remember, don't copy down the plus c because you don't need that for a specific solution, for a definite integral. By the way, you could copy the specific solution in. There's no particular reason why, but why use the general versus the specific. But this plus 4 here, in the next step or two, you'd be adding plus 4 and then you'd be subtracting the plus 4, so it will cancel out, and so it doesn't matter anyway. Alright, so we want to plug pi over 8 into here, and then subtract negative pi over 8 over here. So we're going to do, let's try to do a 2-color system here. Alright, so pi over 8, that's going to be in green. Okay, and then we are going to subtract. I'll do the negative pi over 8 version in orange. All right, now we just got to evaluate this. Now, those of you who are perceptive will remember that cosine is an even function. In other words, if you put a or negative a into it, you get the same answer out. And so that's actually what we're doing here. And so the only difference between these is that negative pi over 8 versus the positive pi over 8, the cosine makes those differences negligible. And so since we've got a negative sign here and this will become a positive sign, then this should all come out to be 0. So you could, at this point, just say 0 is the answer to your definite integral. But and that would be fine. But if you are not quite as slick to realize that, let me walk you through the math here. All right, working over here. Pi over 8 times 2 is pi over 4. The two negatives become a positive. Okay, cosine of pi over 4, that's square root of 2 over 2. Cosine of positive pi over 4 is also square root of 2 over 2. Oops, wrong color. Alright, and you can see now, it should be a little more evident that this is just negative x plus x, or negative q plus q. Whatever it is, these two are mathematical opposites. We're adding them together, and therefore, in the end, you will get 0. And as I've said in previous problems, since the definite integral is the area under the curve, what 0 means is that you have as much area you have as much positive area as you do negative area. In this case, since we're integrating from left to right, we have as much area above the curve as we do below the curve. All right, that's it for the putting it all together lessons.